So when we look at thermochemistry, we're taking careful attention to see that phase changes can be related to a graphical representation. So we know that phases are solid, liquid, gas. To get from a solid to a liquid to a gas, we would add heat. And if we wanted to reverse the roles, meaning that we're starting with a gas, working with a liquid, now we're down to a solid, that would be cooling. So there's a couple of key terms that you need to know to understand that graphical representation the best way possible. So there's two terms here: kinetic energy, which is the energy of motion, or the ability to do work. On the regions, you might see some terms like average kinetic energy, and at this point we'll go over it. AKE, average kinetic energy, they are asking for temperature. Because when you look at a representation of, let's say, a solid or a liquid, they're not all going at the same rate of speed. So it's an average. Some are moving a little bit fast, some are moving a little bit slow, but the majority are working at, let's say, 98.6 degrees Fahrenheit. So kinetic energy, closely related to temperature. Now, potential energy is the ability to do work. It's the potential to do work or to move. So we call this kind of the space between the particles. So when we look at a solid, since there's not that much space in between those particles, we would say that that has the least potential energy. And if you were to look at a gas, okay, just kind of take a look. This is what a solid representation would look like. And this would be what a gas looks like. You can see the space difference. So if it's close together, we're going to say low potential energy. And this one is going to be high. That's an H, potential energy. So why is this important? It's important because when you make a graph, we'll do the example of a heating graph, you need to be able to say, well, where is solid going to start and where is the gas going to start? So if it has low potential energy, we're going to start with a solid, which I'm going to represent by S. So this is all the phase of a solid. And again, what's happening here is we're increasing the temperature. Okay, and we'll put time at the bottom here. So as time goes by, temperature is added. Eventually it reaches this plateau. This plateau is the phase change. Okay, so we'll call this melting, because right now what we're doing is we're doing a heating curve. So we melt it a little while, then it becomes a liquid. Okay. It stays as a liquid for a while until it reaches a certain temperature, which is usually 100 degrees Celsius, that's boiling. And that's going to be the phase where it is vaporizing. Okay. And at that point, it'll become a gas, and we have your heating curve. Okay. So a couple of things. Again, we are heating. Okay, so we are increasing the temperature as we go along. We use the term melting and vaporizing, and we could also kind of put in those key symbols that we've talked about. I think we did it in red. The heat of fusion is represented here, and I think in the other video we used purple. H of V is here. Okay. Now, this was the equation. Q equals M H of V. Do this one backwards. It's the same thing. Commutative property. The very, very first equation that we use, and let me just kind of star them here, is this is when we're seeing the temperature change. So let me just highlight that by using orange. These changes are represented, and we can use the Q equals MCAT. And we can use that for any of those rises. Okay. So how can you remember some of these? That's a lot of information to remember. So let's just kind of identify a couple parts here. Okay. A to B. Let's type it and just put it in as. Okay. We'll say that this is A and this is B. So what's going on there? From A to B, you have basically a rise in temperature. So we would say that we have an increase in kinetic energy. Okay. C to D, same thing. Increase in kinetic energy. E to F, you said it. Increase in kinetic energy. And we can see that because kinetic energy is related to average kinetic energy, which is temperature. Now these horizontal parts, okay, and let me just highlight them again. This part and this part are plateaus, okay? So what's going on here is the temperature is remaining the same. The temperature, no change at all. But what's happening is, and this is where this part is pretty important, B to C, the potential energy is increasing because now you're going from a solid to a liquid, and that space is now getting farther and farther apart. So with that information, we can write in from B to C, we have now an increase in potential energy. Same thing we're talking about vaporization. We're now going from a liquid to a gas where the particles have a lot more space, therefore more potential energy. Okay. So just a summary for diagonal parts, temperature's increasing, average kinetic energy is the same thing, and potential energy is remaining the same, so no change. However, for the horizontal parts, which are those, and I'll say this word often, plateaus. And you could also say the diagonal parts are the rises. And I think they also use the plateaus in math speak as runs. So on the plateaus, or the runs, temperature is no change. Average kinetic energy is the same as temperature, no change, but the potential energy is increasing. And that's what occurs in a heating curve. So what we're now going to do is look at a cooling curve. Okay. It's getting chilly out there. So let's take a look. We have our negative rises. Okay. A to B, we're coming from a gas, right? Condensing to a liquid, condensing to a solid. So A to B, what's going on is that we have a decrease in temperature and a change in, just a change in temperature. Okay, so change in temperature. C to D, same thing. E to F, same thing. Temperature is decreasing, which is the same as average kinetic energy. Potential energy is no change. Now taking a look at the horizontal parts, these plateaus, what's happening is we have from B to C, no change in temperature, but there is a change in potential energy. So no change, no change. Now remember back to what we said about spacing. This has the highest potential energy. That's why this is a little bit higher than that. So as we go from a gas, which has high potential energy, to a lower potential energy, the potential energy is decreasing. So in summary, let's take a look at our 3Ps. 3Ps can stand for plateau, phase change, which means potential energy change. So the 3Ps, plateaus, represent phase change, which shows potential energy changes. So this is a key takeaway. And another key takeaway are what those parts on the graph mean. The diagonal parts, the temperature is changing, okay? So it could either be increasing with a heating curve or decreasing with a cooling curve. Therefore, the kinetic energy is changing. The horizontal parts, no change. However, this is a representation of potential energy that will in fact change. So work on your skills. We'll do a couple practice worksheets. We'll take a look at the heating curve of water.